So far, what we've done is we have recognized how to take a curve that's maybe defined in a standard way, like x squared plus y squared equals 1, and rewrite that in parametric form. In other words, I want to describe this circle with a set of parametric equations. And we found that we could say one way we could do it was say, well, let's let x be cosine of t and y be sine of t. And we could say if we want the entire circle, we could let t go between 0 and 2 pi. So there we have the entire circle. And we have defined that circle parametrically. That's what we've done so far. And we've done several curves this way. We found parametric representations. Now what we want to do is we want to go backwards, and we want to go from a situation like this to a situation like this. And we call this eliminating the parameter. So we want to eliminate the parameter of this set of parametric equations. We want to get back to that x squared plus y squared equals 1. So now, since I'm dealing with this particular set of parametric equations, let's just look at how we would approach this one. Whenever you have sine and cosine together like you do here, and you're thinking in terms of eliminating the parameter, you think about your Pythagorean identity. Sine squared t plus cosine squared t equals 1. This is what you think about. Because notice the process here of eliminating the parameter. I could just say, well, I'm going to take the x squared plus the y squared. Now, what is that? X is cosine, so this is cosine squared t, plus y is sine, so that's sine squared t. See, there's x, there's the y, and I know that equals 1. So following the equal sign, what we have is we have x squared plus y squared equals 1, and we have eliminated the parameter. There, that's done. Now, you could do that. Let's suppose we have this set of parametric equations. Let's suppose we have, let's say x equals secant t and y equals tan t. Let's suppose we have something like that. Now, here we have secant and tangent together. And we remember there is a Pythagorean identity that have those two functions in them. We have tangent squared t plus 1 equals secant squared t. And I could write that as 1 equals secant squared t minus tan squared t. I could do that. So that's an identity there. That's a Pythagorean identity for secant and tangent. Now, so let's look at this. Let's suppose I want to go this way. I want to say, okay, let's go x squared minus y squared, and let's see what that equals. Let's just take a look. So all I'm doing is taking the x squared minus y squared, x because the secant is x, and y because tangent is y. So here we go. We got x squared minus y squared. Well, that is secant squared t minus tangent squared t, and we know that equals 1. That's the identity right there. So here's what we have. We have x squared minus y squared equals 1, and we have eliminated the parameter. So a lot of times, keeping in mind these Pythagorean identities will help you. But let's suppose we've got an expression or a set of parametric equations like this one. Let's suppose we've got t plus 5, and down here we have y equals 2t minus 1, something like that. So here we have a line. We have x is linear, y is linear. Here's the way we can approach this. Pretty simple. We just take one of these equations and solve for t. I'll pick the first one. So I've got x minus 5 equals t. Now that's what t equals. So I want to take that and put it in the other equation for t. So here's what we have. We have y equals 2 blank minus 1. That blank is going to be x minus 5. And there you have it. There's no more parameter. See, I've got 2x minus 10 minus 1. That's y equals 2x minus 11. Now, there's no t in there. I've eliminated the parameter. Now, I didn't have to solve the equation involving x for t. I could have solved the equation involving y for t. Either way, it would have worked out. Okay, let's look at another one. Let's suppose I've got x equals t squared and y equals, let's say, t to the fourth plus 1. Now, here's a way you can do this. You can say, well, let's take this first equation here, and I know that x is equal to t squared. But down here, I've got t to the fourth. So what I can do is I can square both sides. Whoops, t to the fourth, t to the fourth. Ah, so whenever I see a t to the fourth, I can replace it with x squared. So y equals, there's a t to the fourth right there. So I'll replace that with x squared. And there, I've eliminated the parameter. Okay, so this is one really powerful technique. Take one of the equations, get t in the form that will enable you to easily substitute into the other equation. Now, it's not always as straightforward. Let's suppose that we have x equals, let's say, t cubed minus t, and y equals t cubed plus t, something like that. And it might be difficult for us to pick one of these equations and solve for t. So what we're thinking about is, well, what about if I do this? What if I just take y minus x, or you could do x minus y. Let's see what that's going to be. Let's see here. Y is t cubed plus t minus t cubed minus t. There we go. That's it. Now, let's see what we've got here. We've got 2t equals y minus x. That means that t is equal to y minus x over 2. Ah, there we go. Now I know what t is, so I can pick either one of these, like y, for example. In place of t, I'll just put y minus x over 2, like that. Yeah. Oh, this is cubed, isn't it? There. So I've eliminated the parameter. So a lot of times you're just, a lot of times it's very straightforward. Sometimes you're required to use a little bit of cleverness. We used a little cleverness here.